Welcome back, everybody. Hey, it's Veterans Day. Happy Veterans Day to everybody out there. Go thank a veteran. Yeah, let's get into chapter 5, shall we? Okay, so this is section 5.1, chapter 5, section 1. Okay, so let's kind of talk about where we are in terms of the year, right? We started with kind of like a hodgepodge of different things in chapter 1, like a lot of review of Algebra 1, and I said, man, we are in chapter 1 forever. And then we did chapter 2, which was all about linear functions. We learned a lot about linear functions. Pretty much everything that we could possibly do with linear functions, we did in chapter 2. We learned how to add, subtract, multiply, divide them. Well, not really multiply, divide them yet. But we learned how to transform them. We learned how to create the equation. We learned how to graph the equation. We learned everything that there possibly was to do with linear functions in chapter 2. Then we moved into chapter 3, and then things started to heat up a little bit. Chapter 3 was about systems of equations, right? Where we took two lines and see where they crossed, and that's the solution. And then we did a little side step. We did a whole chapter about matrices, and it tied in by way of solving more systems of equations. Didn't really realize it till the end, but that's really where it does tie in. So now we're kind of moving forward this whole key idea of Algebra 2 being exploration in functions. Okay, chapter 5 is is a new type of function, quadratic functions. Now, you spent a whole chapter doing this in Algebra 1, so you have some base idea of what's going on with the quadratic. You may have forgotten a lot of it, and that's okay. It's been almost probably about 2 years since then because you took geometry in the middle. But you should have some base knowledge about it. So what we're going to do today is going to talk about what a quadratic is and what does it look like and how do we transform it based on just the look of the graph. Okay, just the look of the graph. So a quadratic equation is one that forms a parabola. Let's take a look at the parent function. The quadratic function is a function that can be written in this form. Please highlight that, bracket that, do whatever you need to do. That is a pretty important form. We're going to talk about that a little bit more later on, but that is a pretty important equation. That's called Vertex Form of an equation. We'll look at that a little bit later today. That tells us a lot of transformations within that one equation. A times x minus h squared plus k. The main thing in there is that you've got squared, right? That's a quadratic. Okay? You probably think about it as like x squared plus 2x plus 1, like that's a quadratic, yes. That's more in like standard form. Just like linear equations, we talked about slope-intercept form, standard form. You could talk about it as point-slope form. A lot of different forms that you could put it into. This is just one form of a quadratic, a times x minus h squared plus k. The nice thing about this is that it's got all of the transformations right there in front of us, right there. That was a lot of clap. In a quadratic function, the variable is always squared. The table shows the differences between the linear and quadratic parent function. Okay. One second you were here, and then one second you were not, and then you were here. Everybody, Joy came back in the room. If anybody's watching along at home, that's what happened there. Joy came back in the room. And now we're all happier because Joy came back into the room.
So glad I figured that out.
Yeah, there you go. All right, so the difference between the linear and quadratic parent function, notice that every x value is squared to get the y value, right? Every x value is squared to get the y value, right? Y equals x squared. F of x equal to x squared. We notice here that especially in terms of the parent, all of the y values are positive. And I actually shouldn't even say positive. All the y values are non-negative. Because if I just say positive, that kind of knocks out 0, right? So I really should say all the y values are just non-negative. The domain is all real numbers, but the y values are all y values such that y is greater than or equal to 0. Okay? So let's talk about the transformations. We can also graph quadratic functions applying transformations to the parent. So we could make a table if we wanted to, but if we're sophisticated enough, we can understand what's happening within the equation just by looking at it and seeing, okay, this number means this. So that's what we're going to look at here today in terms of translations. So a horizontal shift. Remember, these translations are the same thing that we learned in chapter 1. Same thing that we learned in chapter 2. It means the same thing. F of x is going to map to f of x minus h squared. F of x is going to map to f of x minus h squared. Okay? That is the horizontal translation. F of x is going to map to f of x minus h squared. So that means I'm going to put a plus or minus sign inside parentheses before I square. Obviously, h, that left or right, is the weird one, where if I go left, it's actually going to see a plus inside there. If I go right, you're actually going to see a minus inside there. Now, vertical shift, up or down, well, that's just going to change the y-intercept. So that's going to just add a plus or minus k on the outside. Okay, plus or minus k on the outside. Okay. So these are our rules for translations. Let's take a look at that and see how we apply them. Describe the transformation, then graph each function. Okay, I see two things happening here. Okay, I see two things happening here. One right here, and one right here, and one right here. What's the well, let's go for the easier one first. What's the transformation on 4? Like that plus 4. What is that? Up 4, right? That's an up 4. Okay, what's the blue? What do we think? Since it's inside, it's got to go right or left. So which one? Going to the right. Going to the right. Remember, it's the opposite of what you would normally think. The h value is just 2 because it's x minus h. So the h is 2, so it's actually going to go to the right 2. Now, that means that every single point gets shifted right 2, up 4. Okay, so that means that if I really wanted to go from the parent, because that's my original, let's call that F, my parent. Let's do G in green. I'm going to shift every point using that. So that means that the most important point, 0, 0, the vertex, is going to shift right 2, up 4. And look, it falls like right on that parabola up there. But that right there is like your new origin. Right? Sometimes I tell my students to just do that and say like, okay, that is your new origin. Graph the parabola from there. Okay, right 1, up 1, right 2, up 4. And what am I doing there? I'm just saying squaring the right value and going up that amount. So if I go right 1, I go up 1. If I go right 2, I go up 4. If I go right 3, I go up 9. Right? Right 2, up 4. 1, 2, 3, 4. And then I would go right 3, up 9, but I can't go up to 13. We'll just put it up there. Oh, I guess that goes up to 12. But anyway, and then this reflects over. Up there. Sure. And then I draw my parabola. Okay, the shifting right or left, remember that's one of the rigid transformations that keeps the same shape. So it doesn't affect the narrowness or wideness of the parabola. It doesn't affect the arms of the parabola. It just affects where it's placed on the graph. Okay, let's do that. Do that again. I see 2 again. 2 transformations. What are they? What do we have here? Down 3. And what's the other one? Good. Down 3, left 2. We got a down 3 and then a left 2. Good. This is the left 2. This is the down 3. All right. So that means that I'm going to move the origin point down 2. Or sorry, down 3, left 2. Down 3, left 2. Down 3, left 2. There's my new vertex. So that's like my new origin. And then I say, okay, up 1 over 1, up 2 over 4, up 3 over 9, sorry, over 3, up 9. And then just reflect that, -1, up 1, negative 2, up 4, left 3, up 9. Round it out from there. Now, don't get me wrong. Could I make a table of values to see exactly where this is going to go? Of course. Sure. I know that this shifted left 2, so maybe don't pick negative 2, negative 1, 0, 1, 2. Maybe pick for yourself, I don't know, if got shifted left 2, let's go left 2 more units, like negative 4, negative 3, negative 2, negative 1, 0. Plot those 5 points and see what happens. Guess what? You'll see exactly what we see on the screen here. Okay. Questions about that? All right, let's keep it rolling then. The reflections. Now, the reflections, they're the negatives, right? Those are the negatives. Negative on the inside is a reflection across the y-axis. Negative on the outside is a reflection across the x-axis. Negative inside is a reflection across the y-axis. Negative outside is a reflection across the x-axis. So that means that those values, again, negative then being squared, was a reflection across the y-axis. Now, for our parent, does the reflection across the y-axis do anything? No, it does not. Why? Because when we square the negative, it goes back to the original, right? It goes back positive, okay? Now, that is only for the parent. Or when it's still centered on the y-axis. If the line of symmetry is still the y-axis, then reflecting over that line of symmetry will not do anything to itself because, again, this is symmetrical. Now, if I shift that off the axis, then the reflection would do something, right? Then we would see the reflection. But for the parent, it doesn't do anything. Now, reflection across the x-axis is always going to do something. It's always going to flip it downward or upward if it was already down. Okay, so now we have the the stretches and compressions. Remember, for a horizontal stretch and compression, that's that 1 over b, right? That 1 over bx, right? The 1 over b goes inside parentheses. So again, something that's going inside the parentheses is something horizontal. Anything that's going outside the parentheses is something vertical. So 1 over bx squared is my horizontal stretch or compression. Again, the same rules apply. You know, if it's a 1/3 as my b value, it's going to be compression. But watch out, if I have a 1/3 as my b value, I'm actually going to be seeing a 3x inside my parentheses. If it's a horizontal stretch by 10, obviously bigger than 1, so it's going to be a stretch. 10 would look like 1/10 inside the parentheses. Now, again, vertical stuff is a lot more straightforward. It's just that a times f of x. So if I say vertical stretch by 3, it's 3 times f of x, 3 times x squared, no parentheses. If I see a vertical compression by a factor of 2/3, then it's just 2/3 times x squared, no parentheses. I have to put it inside the parentheses to designate something horizontal. All right. Describe the transformation and graph each function. Now, these are the ones that do not preserve congruency. So these are a little bit harder to tell. Like if I had just given you a graph of the horizontal stretch or compression, it's very hard to tell the number, right? If I give you a graph of a shift, oh man, that's easy. Just count how much it moves left or right on the vertex, you're done, right? But if I give you a stretch or compression, that's a little bit more difficult to tell based on the look at the graph what the stretch or compression is. I don't give you any of those. Yeah. Okay. We don't do that. We don't just go based on the graph and say, okay, what's the horizontal stretch or something? Okay? Because it's really hard to tell. Not very easy to know. Through my marker, Penny. Never. Can I get that back? It's like right underneath your foot. Thanks. I really did that to wake him up. That's what it was. You feel more awake now? Yep. Yep. It almost sounded like a frog. All right, we got 3x squared. What is the Now, do we notice that this would be a horizontal stretch of compression? How do we notice that? Well, it's happening inside the parentheses, so it's got to be something horizontal. And it's not adding or subtracting, so it's not a horizontal shift. So we know that it's got to be a horizontal stretch or compression. Okay, so this is something horizontal. Let's decide what this is going to be. Horizontal. Is this a stretch or a compression? I see a 3, so my first instinct is to say, oh, stretch by 3. Whoa, pump the brakes. Is that really a stretch by 3? No. What is it? Compression by 1/3. That 3 is actually a 1/3. And if it's something by 1/3, if it's less than 1, it's got to be a compression. Because it's the reciprocal. Remember, the rule is 1 over b. So if I say I say 1 over b ends up being 3, right? That's the number. 1 over b is multiplied to x. So if 1 over b is really 3, well, just a little manipulation. Multiply by b, divide by 3. 1 over 3 is my b value. Which means that tells me that it's a compression. All right. So what does that mean in terms of my graph? Well, does it change the origin point? Does a horizontal compression change the origin point? No. Because remember, anything horizontal is going to affect the x value. How much? Multiplied by 1/3 in this case, right? So if I take 0, 0 and multiply 0 by 1/3, is it going to do anything? No. So I know that this point's going to remain the same. Okay, what about this old point 1, 1? What's that one going to look like? What's 1, 1 going to look like? What's 1, 1 going to look like? Well, if I horizontally compress this by a factor of 1/3, if I plug in, if I take 1, 1, that's actually going to be, look, well, I guess we should do this. 1, 1 is going to turn into, well, horizontal compression, multiplying the x by 1/3, 1/3, 1. Right? 1/3, 1. Okay, well, what if I take this point, 2, 4? What would that one turn into? Well, same thing. Multiply the x by 1/3. The x was 2, so it's no longer 2, 4, but 2/3, 4. 2/3, 4. And those will reflect. Take another one. This one's a little bit easier to compute. What if I had said 3, 9? What would that point turn into? What would that point turn into? Somebody tell me. What would it be? 1, 9. Because 1/3 of 3 is 1. So this would be 1, 9, which makes sense. And it makes sense because what would I get if I plugged in 1? 3 times 1 is 3, squared is 9. Okay? So that's how we can do that if we'd like to. Okay? Now, for our purposes here, I just want to make sure that you know that it's going to be narrower. Okay? I just want to make sure that you know it's going to be narrower. A number inside the parentheses, a whole number, is going to make it more narrow. A fraction on the inside is going to make it wider. A whole number on the outside, well, I think we talked about that on the next one. Now, could I have made a table of values to graph this? Of course. Of course, make yourself a quick table, XY table, -2, -1, 0, 1, 2, -6 squared, 36, -3 squared, 9, 0 squared, 0, 1 times 3 is 3 squared, 9, 2, 6, 36, right? Quick table, for sure, totally fine. Could I have put this on my graphing calculator? Yes. Let's go ahead and get out our graphing calculator. me show you here. If I go into my y equals, get that out of there, and say parentheses 3x parentheses squared, I'm going to hit zoom 6 because I don't, oh, sorry. I'm not sure where my calculator's been. Ah, do we see it there? A really narrow parabola. Right. If I really wanted to, could I plug in my parent as well? Just the x squared? Sure. Do we see how much more narrow it is than the original? Okay. Could we also find the table? Yes. Take a look up above graph. There's my table, which is one that I almost created right here, right? Negative 2 comma 36, negative 1 comma 9, 0 comma 0, 1 comma 9, 2 comma 36. The y1 in this case, my y1 is my new, my original is the y2, the parent is the y2. Right? If I square negative 1, I get 1. Square negative 2, I get 4. Square negative 3, I get 9. So on and so forth. Okay, well, let's take a look at the next one there. So a lot of different ways that we could graph this. I see two things happening here. It may only look like one, but I actually see two things that are happening. What two things are happening? What two things are happening? Okay. Good. Which way? Good. Reflection over x. And we see that because the negative on the outside is a reflection across the x-axis. Okay, what's the 1/2 do? What's the 1/2 do?
Vertical compression by 1/2.
Yeah, very good. Vertical compression by 1/2. I know it's vertical because it's happening to the outside. How do I know it's happening to the outside? Because there's no parentheses. Right? It's not being, that 1/2 is not squared. The 1/2 is sitting out front. We know it's a compression because it's a 1/2. That one's simple, straightforward, vertical stuff. All right, so now we see two things. It's a reflection over the x-axis, and it's a vertical compression by 1/2. Now, vertical compression, it's going to reduce the y value. So if I just flip this over the x-axis, it would look like this, right? That's just flipping it over the x-axis. But then, if I would have vertically compressed it, that means that every y value gets halved. So the -1 turns into that. The -4 condenses down to the -2. And then same over here. So this is my final. Okay? The red is my final. Vertical compression will actually make it wider. Okay? A vertical compression will actually make it wider, not narrower. A vertical stretch will make it narrower. And think about it. Think about it logically. Vertically stretching it out, that's going to make that more narrow. Okay. A couple other things here left to do. A couple more slides. Sorry, I told you you were going to get time to study. I'll be quick. This is true vertex form. This kind of like rolls it all together here. A times x minus h squared plus k. This kind of puts all the transformations into one equation. There's only one transformation left out, and it's the horizontal structure compression. The a value indicates two things actually. If there's any reflection happening to it, I'd say a reflection across the x-axis. If there's any reflection across the x-axis to it, as well as any vertical stretch or compression. The h value, the thing that's being added or subtracted to the inside, that's a left or right. The k value, that's the thing that's moving it up or down. The nice thing about vertex form, why is it called vertex form? Well, because you can easily identify the vertex. The vertex is h comma k. We're going to be using vertex form a lot. This is really easy to graph, given vertex form. It's really easy to write the equation as well. Like for example here, the parent function is vertically compressed by a factor of 1/3, translated 2 units to the right, 4 units down. Okay, vertically compressed by a factor of 1/3. That means my A value is 1/3. Then translated 2 units right. Okay, H is 2. And then 4 units down. Oh, that means K is -4. So literally all we have to do is put it into, we're calling it G of X, is equal to A times X minus H squared plus K. Okay, well that means G of X is equal to 1/3 X minus 2 squared, oops, not plus a -4, just -4. And look at that. Just based on the transformations, I made the equation. We're going to go through great lengths to make it an equation in standard form. Man, is it easy to make it in vertex form. As long as you know the transformation. Okay, one last problem, I swear. One last one. On Earth, the distance d in meters that a dropped object falls in t seconds is approximated by d of t is equal to 4.9 t squared. That's a distance as a function of time. The displacement function. So 4.9 t squared. On the moon, the corresponding function, distance on the moon, d sub m of t, is 0.8 t squared. So that 4.9, that acceleration due to gravity, is reduced, right? What kind of transformation does that describe? And what does it mean? What type of transformation is that? What reduces the number being multiplied on the outside? What do we think? 4.9. And turn it into 0.8. Is that subtraction? That would be division, wouldn't it? That would be division. So like, or in other words, multiplying by a reciprocal, right? So I want to take 4.9 and make it 0.8. So I'm saying, okay, 4.9 times what is equal to 0.8? That's a point. Right. I want to know what that value is. How much did I actually have to divide it by? Multiply by some sort of reciprocal. Okay, well, just to solve for my question mark here, 0.8 divided by 4.9 is this decimal. Let's see if that turns into a fraction. 8/49. Sure. 8/49. I guess we just moved the decimal place 1 unit. So this value that I'm multiplying by is 8/49. Okay, that took d of t, d of t, and transformed it into d sub m of t. How did we do that? Well, we changed the value. We multiplied a number on the outside. We multiplied this value, 4.9 t squared. We changed it by taking 8/49 of d of t. That got us equal to d sub m of t. Okay, what multiplies on the outside? What is that transformation that multiplies on the outside? Oh, somebody tell me, come on. What multiplies on the outside? Vertical compression. Good. A vertical compression. And we know it's a compression because it's less than 1. So we could say that this is a vertical compression by 8/49. Vertical compression by 8/49. I could give me that. You could give me that decimal too if you really wanted to. It's a word problem, so decimals would be okay. We normally see this fraction though. And what does that mean? Well, logically, that means that there's less gravity, right? The acceleration pulling down toward the moon is less. How much less? Less by a factor of 8/49. Okay? It's 8/49 of the pull. Okay. All right. Everybody say bye to the folks at home. That was enthusiastic. They really miss you. They told me before I started the video. I swear. All right, see you folks.